Good evening, everybody, and welcome to the Museum of Science. We are thrilled to present tonight's program and pleased that so many of you were interested in attending. And we are happy to announce that C-SPAN is here videotaping the program as part of their book TV series, and you'll be able to catch the program on television sometime in the upcoming weeks. Not long ago, the question of parallel universes wasn't one of science, but one of science fiction. Now, as I introduce our special guests, I'm actually wondering whether there's another version of myself doing just that in another universe, a parallel universe that's not too different, but also not altogether the same as ours. In fact, an infinite number of versions of ourselves may be gathered at the Museum of Science to hear about the possibility of whether these other universes exist. It's puzzling. Brian Greene is widely recognized for a number of groundbreaking discoveries in superstring theory, the idea that minuscule strands of energy vibrating in at least 11 dimensions create every particle and force in the universe. A math prodigy and a Rhodes Scholar, Brian Greene currently is professor of physics and mathematics at Columbia University. He has described his objective as enabling the general public to see science as a living, breathing, evolving undertaking. And he has certainly accomplished that through his popular three-part Nova series, The Elegant Universe, and his best-selling books. Brian speaks tonight with Dr. Amir Axel, mathematician and author of a number of popular books on the history of mathematics and science, including the New York Times bestseller Fermat's Last Theorem. For his latest book, Present at the Creation, The Story of CERN and the Large Hadron Collider, Amir interviewed the world's top physicists. So please join me in welcoming Brian Greene and Amir Axel.
Well, good evening. It's really a special pleasure and honor for me to welcome Brian Greene to our fair city. And before we start talking about other universes, why don't we start talking about you? I know a lot of people would like to know some personal details about you. I understand you're a vegan?
Yes. In this universe, I am. That's true.
You stole my next question.
Sorry.
Whether you're a doppelganger or a mediator.
It's very
Maybe.
disturbing to think so, but according to our understanding, that's quite possible.
I was on an airplane just a few days ago, actually coming from London, and a woman next to me, I ordered vegetarian. She said, "Would you be offended if I ate meat?" And I said, "I don't care what you eat." But anyway, I see you're offended by your doppelganger. So,
but he doesn't sit next to me on airplanes. So,
oh, good.
So it all works out.
Well, if you're of the kind I'm thinking, you'd both disappear if you sat next to you in an airplane.
That's possible, too.
So, tell me something else. I understand you have a number called, what is it? Erdos something else?
Oh, the Erdos bacon stuff.
Yeah, can you explain about that?
Yeah, you know, there's this idea of how many degrees of separation you are from famous people. So the original one was how far away a given actor was from Kevin Bacon. And then mathematicians wanted to compete and have their own version of Kevin Bacon, which is Paul Erdos, who collaborated with many, many mathematicians. So the question is, how far are you away from having written a paper with Erdos? And then people said, well, let's put it all together and see how far away a given individual is from Kevin Bacon and from Erdos. And as you can imagine, there aren't too many people that sort of are close to both, but there are a handful of us. So I'm one of them.
How many are you?
Well, I used to be the world leader in.
What's your number?
It's number 5, but I've been overtaken.
You're 5 and what?
Well, 5 total. I think it's
so you add
2
the 2.
from Erdos and 3 from Bacon, or something like
good.
that. But I think like Gwyneth Paltrow has taken over the lead.
Is that right?
I don't
She's
know.
a
She wrote a paper with.
She's a mathematician.
Yeah, something. No, I'm not sure, but there definitely are people who've taken over.
I see. But in another universe, you have number 1.
Yeah, that's always going to be the case. Yeah.
So, what is this? let me ask you, we all think that there's one universe. How could there be more?
Yeah, well, that is the essential question to start with. Because, a long time ago, 2 years ago, the word universe meant just what you are saying. It meant everything, the totality, every star, every galaxy, the whole shebang. So what sense could there possibly be in having more than one everything? Mm-hmm. And what we have found in research that actually dates back a number of decades, but most vigorously relatively recently, is that our mathematical investigations are suggesting that what we have thought to be everything may actually be a tiny part of a much grander cosmos. And that grander cosmos can contain other realms that seem to rightly be called universe, just as our realm has been called universe, which means that you have many universes, multiple universes, which we call the multiverse.
Sounds like a brand of cereal to me, multi-cereal or.
Well, you have a food thing going on here, don't you?
No, don't we? So tell me, I understand that physics is a science, experimental science.
Yes.
So where does this come in? I mean, it sounds more like a religion to me. I mean, there's this universe and another universe. I mean, how do we learn about these other universes?
Yes. So how can you gain confidence in an idea that speaks of realms that we can't see, mm-hmm. that we can't touch, we can't visit, right. we can't observe directly? So let me give the answer in two parts. One is, in some versions of the multiverse, and I should emphasize there's not one proposal for how there might be many universes, there are a number of proposals. In some, there can be subtle connections between the universes that might allow us to have some experimental window onto them. But hold that to the side for the moment. Let's think about the ones where you couldn't visit them. Well, why do we think about these things? Well, we have a belief founded upon really hundreds of years of experience that math can provide a gateway to reality. It can provide a window onto a reality that at the moment the math is being done, we can't actually see or observe that reality. I mean, Einstein is the greatest example, right? He wrote down his equations of the general theory of relativity way back in 1915. Others looked at those equations and found that they seemed to say the universe should be expanding. The math said the universe is expanding. Einstein himself said, no, I don't actually believe that. But 12 years later, observations showed the universe is expanding. The math was confirmed by observations. Other examples are black holes. Again, Einstein's math gives rise to them. Einstein didn't believe it. Observations now show that there are black holes. So we're following in that tradition. We are doing mathematical equations, following them, and as we can discuss in some specific cases, they are leading us root by root to the possibility that ours is only one universe. Does that mean the math is right? We don't know. It has to be confirmed ultimately through some kind of observation or experiment, but the possibility that the math is revealing this new picture of reality is sufficiently compelling that many physicists, including me, are taking it seriously and investigating it vigorously.
But I think the operational word here was can, because mathematics is not physics.
Exactly.
So sometimes the mathematics works and sometimes it doesn't. You don't have to go very far, but if we go back, you can say the epicycles were invented by a mathematician, a Greek mathematician, and then Ptolemy used them to argue that the Earth is the center of the solar system or the universe for him. So here's mathematics that's valid as mathematics, not very complicated mathematics, but mathematics nonetheless.
Yes.
That doesn't describe reality. And you can go to later on. For example,
before you leave that example,
sure.
Because I think that is a great example where you had some individuals who were looking at the motion of the Earth and the motion of the planets and coming to certain conclusions that we now know to be erroneous, but conclusions about how things were working. There were other physicists, mathematicians, who looked at that math and said, this is so complicated, this is so convoluted, and if we look at the math this way, it all simplifies, but the conclusion is that the Earth is not the center. So we were propelled by mathematical investigation to imagine the Earth is not the center. And then others, using similar kinds of reasoning, noted that the sun is actually not the center either. And then similar mathematical reasoning showed us that our galaxy is not the center. It's one of many, many galaxies. We've gone through a sequence of, if you will, cosmic demotions. By following the math, confirming it through observation, we may be on the threshold of the next demotion by following exactly the same pattern. Earth is not the center, sun is not the center, galaxy is not the center, our universe may not be the center. It may be one of many universes following exactly the same pattern.
But I think the key is that the mathematics is always simpler in a sense for Occam's razor or something like that.
That's certainly what we have found.
But when you do very complicated mathematics and you trust your equations, often these equations are cumbersome and
I wouldn't say so. I mean, I can understand where you might come to the conclusion because if we get into any of the details, you know, some of the multiverse ideas come from string theory, which seems like a complicated subject when you hear about its features. But when you look at the equations of string theory, the starting point, it's actually pretty simple.
So how many string theories are there?
There's one now. I mean, there was a time when we thought there were a handful of distinct string theories, but wonderfully, in the last decade, the math has come together and we've realized that what we thought were different theories are actually all the same, just expressed in a slightly different language. So everything has been simplifying. You know, if you take even a good example, Darwinian evolution. The principles of evolution are pretty straightforward, right? But nevertheless, those principles can yield the rich variety of life that we see on Earth. The outcome can be complicated, even though the starting point is simple. That is the way I would characterize our thinking about certain modern physical theories. The outcome, say string theory, again, if we get into it, extra dimensions, vibrating strings, you know, it seems complicated, but that's like the richness of life coming from evolution. The starting point of string theory, like the starting point of evolution, pretty straightforward.
I see. So tell me, what are some of these theories that lead to the multiverse? In your book, you describe several of them. I couldn't find the one with the anti-universe. That's my favorite, actually, where your anti-person, you know, is, you know, positrons and anti, you know,
Watching
protons.
too much Star Trek
Yeah,
or something
right.
there.
So do you favor that route to the multiverse?
Well, there are many ways to the multiverse. Maybe a good place to start would be what I consider the simplest route of all, which is to imagine the possibility that space goes on infinitely far. Right? If you were to get into a rocket ship and head out into the cosmos, would you at some point hit a brick wall? No, most of us don't think that's the case. Would you circle back to your starting point, like what would happen on the Earth's surface if you took a similar journey? That's possible. Or would you simply keep on going forever? We don't know, but let's take that third possibility seriously. If we do, there's a startling conclusion, and it's simply this. In any finite region of space, matter can only arrange itself in finitely many different configurations.
Very
Particles.
large, very large.
Large
finite,
number, but a finite number.
finite.
Similarly, like if I take a deck of cards.
Sure.
If I shuffle the deck, the order of the cards differ. There are only finitely many different orders of the cards, many different orders, but still finitely many. So if I shuffle the deck enough times, infinitely many times, the order of the cards has to repeat. Similarly, in infinite space, the order of the particles, the configuration of particles has to repeat too. Now, what would that mean? Well, as we heard in the introduction, it would mean something pretty strange. You see, you and I were just a configuration of particles. Everybody in this room is just a configuration of particles, as is the Earth and the Sun and so forth. If the configuration of particles repeats someplace out there in the cosmos, it means all that we know is repeating.
Yeah,
we are out there. And
right.
that's a very straightforward mathematical conclusion from a simple starting point. Space was on infinitely far.
But you're leaving out an important thing. The measure of that is zero when you go to infinity.
It doesn't matter.
So the probability of us speaking in another universe is, do you want to go there?
Absolutely. In fact, I don't need to frame it in probabilistic terms. Let me just do it in a more concrete setting. If I had that deck of cards, and I shuffled it over and over again, do you agree that sooner or later the order of the cards will repeat? Not the probability. I'm not saying...
The deck is too large. That's
no, it's 52
really
cards.
Deck. No,
52
well,
cards.
That's easy. You're taking the easy way out. I'm talking about the universe,
No,
not
but
about
you're discounting the power of infinity.
But
infinite space. This is the supposition. Now, you can challenge that, but let's not, just to get to the end of the argument. If you take on board this idea, which I think most cosmologists and physicists have, that space goes on infinitely far,
No.
then you've got a lot of room for this to happen, and that's the point.
I have a problem with space going infinitely far.
Okay, that's fine. That's a good place to try to poke a hole in this.
In mathematics, dimensions go infinitely far. But in physics, the way I understand physics, these three dimensions in which we live, and the fourth of time, which Einstein taught us, is related to the other three, was created in the Big Bang. So I think if you think as a physicist, and check me if I'm wrong, space here was created in the Big Bang. We're not expanding into another space. We're creating space as we're going out. As the galaxies are expanding with the 13.7 billion years and so on, we are creating three space or four space. So where's the other universe when you're, as a mathematician, okay, there's this dimension, it goes on forever, call it X, and this Y, and this Z. But I think in one of your universes, you got a universe here, and one here, and one here, and one here, and one here, and infinitely many of them, that's okay. But does it really exist from a physical point of view when space was really, space and time were created in the Big Bang? So
right. So I do need to correct you a little bit, with all due respect.
That's what I'm here for.
So there is an incorrect image that many people have in mind, which is this. When we think about the Big Bang, typically we imagine that further and further back in time, the entire cosmos was smaller and smaller and smaller. And way back toward the beginning, the universe we sort of intuitively think of as very, very small, and then run that film forward, and as you're saying, space is created from that Big Bang, so how could it ever be infinitely big if it was very small in the past? And if that were the right picture, you would be right. But that was not the picture that's compatible with an infinite universe. In an infinite universe, as you head ever further back in time, the universe is still infinitely big. If you go back in time and the universe is half as large as it is today, half of infinity is still infinity. If you go back further, 1/3 of infinity is still infinity.
But what does infinity mean here?
It's the traditional one, having unbounded.
The universe is infinite?
That's infinitely big, yes.
So what's the radius of 13.7 billion years?
That's the observable universe.
So the universe goes beyond that?
Absolutely.
So what's a Big Bang?
What's
a Big Bang?
That's the key point.
What is the Big Bang?
The Big Bang is an event that gave rise to our realm, but if the universe is infinitely big, then our part, the part that we have access to, is only a piece of the entirety. So you need to make
and the others are expanding as well.
Exactly. So you need to make a distinction between the observable universe and the entirety. The observable universe is just the part that we can see. And you're right, we can't see further back than roughly 13.7 billion light years because that's the amount of distance that light can travel since the beginning. But almost nobody believes that the universe ends at that point. Most everyone believes it goes on at least a far distance beyond that. And the supposition of this particular example that we're saying is that it goes on infinitely far.
Brian, you're a magician too. You pulled out infinity out of the hat, as it were. I mean, what does infinity have to do with anything here? Everything we learn about physics is really finite. What does infinite mean? What cardinality does it have? Does it have the cardinality of the integers or the continuum or the space of functions? I mean, to invoke infinity, you have to give me something.
Yes, and the most straightforward definition would be it's the same cardinality as the real line. It's just the real line extended in exactly the way that you know about from when you took mathematics at a young age. So it just goes on without bounds. So let me ask you this. Let me turn it around.
Okay.
If the universe is not infinitely big, what happens when you travel out?
Well, look, I interviewed Steven Weinberg a few months ago about cosmology, and I asked him, the Big Bang is believed to be a quantum fluctuation. That's what created our universe. What was it a quantum fluctuation in? What was the medium in which we were spawned, if you will? And he said, that we don't know. We can't go there. We don't know. So, but you're telling me something else. You're telling me that there's an infinitude of space. As mathematically, I agree with you. The real line exists, but it exists platonically in a mathematical.
No, I'm asking a very concrete question. If you build a spaceship and you go out and you just keep on going, what happens?
Well, if I take physics the way physics has been done, here's the Big Bang. It started here, but it has there's no location has no meaning. you can't define that point as being located in space because space doesn't exist before the Big Bang from the universe we can see. I don't know about other universes. So if you start here, this space was created with the Big Bang.
So if you go into a rocket ship and you head out into space and you keep on going, what happens?
You can't. You know that you can't. You can't.
What do you mean you can't? You have a ship and you go out.
Well, you
Here are the possibilities. You hit an end.
No.
You cycle back to your starting point. No.
Brian, you know pretty well. If you aim a telescope in this direction at night, and you aim a telescope in that direction at night, the two parts, take the farthest galaxies you can see, they're receding at the speed faster than light because of the accelerating expansion. Well, because of the expansion of the universe, you don't even need acceleration. So that part doesn't talk with this part. How are you ever going to get from one part to another with a spaceship that travels less than the speed of light?
So if you get in that ship, what will happen?
I don't know what will happen. I'll be lost in space.
Right. So, it's a mathematical question, which in math language would be, what's the topology? What's the overall topology of space?
That's where I disagree with you. I think topology exists in a mathematician's mind as a Platonic kind of thing, the way varieties or motives or things that may have nothing to do with the real world.
Well, this is
because
a good point.
when you, as a physicist, take parts of mathematics, you actually finesse my key point, which is mathematics is not physics.
Good.
A lot of mathematics here doesn't do anything for us. I'll give you an example.
Yes.
We talked about those epicycles. I'll give you, I'll take your glass, I'll give you another example.
Yeah.
So Werner Heisenberg, whom I actually met at Berkeley in 1972. Yeah, fill it up.
Good. No.
I want it filled up to the same level, if you don't mind. Yeah.
Okay.
So we've got, Werner Heisenberg was one of the fathers of quantum mechanics. And in the 20s, he built this theory that everybody knows about the uncertainty principle and maybe also about matrix mechanics. And then he went a step further. And he thought he's going to go into something else. And he said, here's a proton, and here, I need 3 ice cubes here and 3 there. Anyway, so you've got, we've got the proton and the neutron. He said, there's a symmetry between them. There's a proton, a neutron. I'm going to use the mathematics of symmetry to explain why these two are so similar. And he called it SU2, which, of course, you know. And then we won't go where it went from there, but that assumption was wrong. That was taking mathematics that makes a lot of sense in your mind as a mathematician, but has nothing to do with the real world in the sense of the proton and the electron. They look very similar just because of an accident of nature, because the quarks are so small, so to speak. Yes. One of them is a lot heavier than the other in absolute terms, but when compared to the mass of the two, then you think they're really very, very similar. And he went into symmetries. Now, of course, you and I know that Young and Mills then went later and took SU2 and added U1 and did all kinds of things. And the mathematics sort of came back. But at that moment, what you have as mathematics is very powerful and absolutely useless.
Yes.
Yes. I rest my case.
No, it's a... but it's a case that I agree with. What I would say is mathematics opens up the realms of possibilities. So thank you very much. And what the art of physics is being able to sniff out which mathematics is relevant for reality and which mathematics isn't. Now, experiment and observation are a key part of that story. And the one that you just mentioned, ultimately it was observation and experiment that dictated that math wasn't the right direction to go. So what we need to do and what we spend our professional lives doing is trying to understand which body of mathematics is relevant for reality and which isn't. Now, in this particular case that we were talking about, the argument makes the assumption that a certain body of mathematics, that space can go on infinitely far, is relevant to reality. If that's not right, and it may not be, I'm the first to say that it may not be, but if it is, you come to this startling conclusion. If it's not, then you don't. And I think that's the mode of thinking about many of these multiverse proposals. Many of them start with a certain mathematical framework, push the math as far as we can to the border of understanding, and then use the math to look over the horizon and see what's there. Are we seeing reality or are we seeing mathematical ideas? That's a question ultimately that has to be confirmed or disputed by observation. Now, let me just give you an example where that mode could help us here. So people have asked themselves, if space doesn't go on infinitely far, could we perhaps observationally establish that? That would be a nice thing to do. Well, one way to do that is, if it doesn't go infinitely far, and if it does have the shape like the surface of the Earth where it comes back on itself, well, then as you know, there are structures in space that give off light, galaxies, the cosmic microwave background radiation, and so forth. If the universe has that shape, light that comes from a distant source can hit our eyes, but it can also pass by us, circle around the universe, and come back a second time or a third time. So if you can see multiple copies of a given object, that would be a nice piece of observational evidence showing that space is finite. No such evidence yet. That doesn't mean it's infinite. Could be big, so big that it hasn't had time to cycle around. But that's exactly what physics is about. Doing theoretical physics, doing mathematical calculations, pushing to the limit, and then trying to find observational tests.
Right. So tell us about some of these specific theories. Let's start with the one I dislike the most.
Yes.
How about the many worlds? Many worlds.
Many worlds.
I can't even say.
Many worlds is a somewhat different character of proposal for how we can be one of many universes. And you may note that in the book, it's actually one of the later chapters because...
Yeah, I was worried about that. Why is that?
Why is it later? You're right, it's chronologically it's the earliest, that's right.
Yeah.
Because I think in thinking about this subject, marching through the developments chronologically doesn't give you the most pedagogically sensible way of thinking about where we are today. Because, in particular, the many worlds approach of quantum mechanics stands outside the chronological march that ends up with some of the ideas of string theory. But it is an interesting proposal, and that's why I have a chapter devoted to it.
It's weird, though.
You're right, it is weird, and you'll note that in that chapter, I basically come to the conclusion that I don't think it works. But that doesn't mean it doesn't. And if you're talking to other people, like David Deutsch from Oxford, or various other researchers, David Wallace and so forth, they would sit here and say it absolutely does work. So I don't want to give the wrong impression that there's a consensus. Well, here's the idea. So the new idea of quantum mechanics in the early part of the 20th century was that whereas Newton said, tell me how things are today, and I will predict how they will be tomorrow. The universe is like a giant clockwork. I'll use my mathematics to turn the crank forward and predict how things will be. And the observations established that that way of thinking about things was very accurate when applied to everyday objects like glasses, or to the moon's motion, or to a rock that you throw. Newton can tell you what will happen. You do the observation, and it does happen. Great. When people began to probe the microscopic realm, that whole structure began to fall apart.
Different universe there.
Completely different universe, completely different realm. I don't want to, let's not, use the word universe in too many different ways tonight, but a completely different environment. And in some way, you shouldn't be so surprised. Why should the laws that work on everyday scales also work on tiny scales? And it turns out that they don't. The new laws, the laws of quantum physics, and the new idea of quantum physics is that you can only predict the likelihood, the probability of one outcome or another. So if I'm not dealing with a rock or the moon, but an electron, and I want to know where it is, the quantum laws say, well, there may be a 50% chance that it's over here, and a 50% chance that it's over there.
Or both.
Or, well, no, let's just consider that situation.
Fine.
There's a 50% chance of each, and you can't do any better than that, according to quantum physics. Now, the weird thing is, when you do an observation of the electron, you always find it either here or there. You never find it sort of half here or half there. There's never sort of some melding of the two. So the puzzle has been, for 80 years, even though the probabilities of quantum mechanics are confirmed by doing an experiment over and over again, finding the electron 50% of the time here and 50% of the time here, how do you go from the fuzzy, hazy, probabilistic mathematics of quantum theory to the single definite reality that we observe when we do an experiment? Nobody has answered this question yet. Shockingly, it's 2011. No one's answered this. But the proposal that comes from Hugh Everett in 1957 is this. He says, look, if the math says there's a 50% chance the electron could be here or here, he says when you study the math diligently and really follow it through, and apply it to the experimenter as well, the math seems to say that when you do the observation, you find the electron here, and you find the electron here, just in two different universes. In each universe, there's a copy of you thinking incorrectly that there's a single definite outcome, but from the bird's eye view, there are two of you thinking that, And that's just a single example with an electron. The idea is that all of the possibilities allowed by the quantum laws are realized in one universe or another, in this grand collection of possibilities that we call the quantum multiverse. That's the idea.
But you believe it?
No, I don't believe it. I don't believe it because I don't think that we've established yet in any of the analyses, and again, this is controversial. Some people think we have.
Yeah.
I don't think we've established yet how this way of thinking about quantum mechanics actually describes our observations. That link, I don't think, has been established.
I think we just don't understand quantum mechanics. And
well,
most physicists agree with
that. No, but that's tantamount to exactly the same statement. To understand quantum mechanics is to say, how does quantum mechanics link up with observation? And I don't think we've answered that yet.
Well, it just doesn't appeal to our understanding of the universe because we are living in a space where things don't happen the way they happen in the micro world. No, but let me ask you
let me just give a small footnote to that.
Yeah.
That's why
mostly, except for Bose-Einstein condensate, things like that. Sometimes you can see large objects behaving quantum mechanically, but very, very rarely.
You know, I wasn't going there. I just want to emphasize that what you're saying explains why quantum mechanics is counterintuitive.
It's worse than that.
Well,
it's crazy.
Whatever word you like. Whatever word you like.
Einstein couldn't accept it.
Exactly right. But why is that? And there's two parts to that story. There's
Why
two
is
parts.
that?
No, I wasn't actually asking you a question.
No,
that was rhetorical.
but I want to answer it.
You know, there's a part of quantum mechanics that feels very uncomfortable because it's so at odds with experience.
Right.
And that's the part which makes it hard to accept these crazy ideas.
Right.
But if these crazy ideas have been fully worked out mathematically and the link to observation has been made, which it hasn't yet, then we'd have to accept that our intuition has been built up from thousands of years of living in a world of this size, and there's no evolutionary advantage to understanding the probabilistic motion of an electron. When you're out on the savannah trying to get your next meal, it doesn't matter if you understand the probabilities of quantum physics. It matters if you understand Newtonian dynamics of where that animal's going to be in 5 seconds so you can jump it and eat it. And that's why our brains have developed to really be Newtonian. If I took this glass, okay, and I take the water out and I threw it, somebody could catch it. They would be doing the Newtonian calculation because it's intuitive. If I were to do the same thing with an electron, they wouldn't be able to catch it because they don't have that same intuition. That's only part of the problem. The real problem with quantum mechanics is not that it's counterintuitive or crazy, it's that there's a real puzzle that we haven't answered yet. How do you go from the probabilistic math to the definite reality? That has not been solved.
But Brian, why do you have to? Are you a gambling man?
Why do you
We talked
ask?
about your food habits. Do you gamble? Well, have you been to a casino?
If it helps,
have you been to a
happy.
casino? Never?
Yes, yeah, I've been to a casino.
Okay, so in a casino you have like a roulette wheel or something like that, and it rolls around, rolls around, and it falls at one number. There are 36 numbers and 0 and 00, but it chooses one number.
Yes.
Do you have a problem with that?
Do I have a problem with that? I didn't think I said
do you have
I
a problem
did.
with
No.
that? Okay, why do you have a problem with the probabilities for the electron?
Oh, I don't have a problem with a description of the world that's based on probabilities.
Yeah, okay.
I do have a problem with a theory that is incomplete. And that's our current understanding of quantum.
Then you're Einsteinian.
No. Einstein's
He
problem
said it's incomplete. He said the theory is incomplete.
for a different reason. Well, Einstein's problem with quantum mechanics had to do with...
Well, it had to do with a lot of things, non-locality and the probabilistic
Exactly.
and interpretation and all kinds of other things. Even though he had the vision to actually understand, you know, something we call today entanglement and things
Yes.
like the EPR paradox and so on. But what I'm
Yes.
asking you is something at a lower level. You have no problem going to Las Vegas. Well, maybe you do. But gambling, you have no conceptual problem as the guy on the prairie hunting mastodon or whatever.
Yes.
You have no problem with the wolf or whatever you're hunting going one way, and then another time you're chasing an animal that's going the other way. That's Newtonian in a sense, right?
Yes.
What you're talking about. Would you really have would you need to see a shrink if the wolf went one way and next time it went the other way?
If the wolf looked like my mother or father, I might go to the shrink. But I'm
you have
not
no
sure,
problem with it. Why?
But I'm not sure the point you're making.
Okay, here's my point.
Okay.
You do an experiment, and when you can observe it,
Yes.
when you open the box, the electron goes one way. It can be to the right, And in another universe, so to speak, another time you do it to the left.
Yes.
But when you don't, the electron goes both ways.
Yeah.
Right? We know that because we can think quantically. We are not Neanderthals, right?
I mean, if we're trained in quantum mechanics.
Yeah,
sure.
if we are, it's okay for us.
Right.
Box is closed, goes both ways, and interferes with itself. Typical Young experiment with one particle, right? You have no problem with that at all. When you open the box, you collapse the wave, so to speak. You toss the coin, you roll the roulette wheel, and it goes one way or another. Why is it? And by the way, the problem is not of mathematics, and you know that. Hilbert space does it all for us. For a mathematician, Hilbert space operators and whatever.
Just to get a sense, how many people are familiar with Hilbert spaces in this room?
I was talking to you.
No, but I think we're going a little bit far afield. So let me just be a little bit clear here. My problem with quantum mechanics has nothing to do with the fact that it involves probabilities.
Oh.
So I'm happy with probabilities.
So there are no more many worlds.
You somehow we're
that's
talking
the
at cross
alternative.
purposes.
That's the alternative to the probabilities.
No, absolutely not.
Okay.
The people who believe in many worlds also believe in probabilities. They're just trying to make a link between the probabilistic predictions and the fact that when you make an observation, you see a single definite reality.
Okay.
And that link is a subtle one that has resisted solution now for about 50 years. So if you were talking to a person who does believe that there are many universes in quantum mechanics, you would ultimately find that they're trying to explain the very same probabilities that Niels Bohr was trying to explain back in the old days. So it's not like Einstein, where Einstein had in his mind that physics needed to make definite predictions. No, we've long since gone beyond that because observations do show that the probabilities work. We're trying to close the gap in the actual quantum formalism. But my suggestion is that we move on from this because this is simply one variation on the theme of multiverses.
What's your favorite multiverse?
You know, it depends the way in which you judge favorite, but I certainly have a leaning towards those that have a chance of being experimentally tested in the shortest time frame, which is one way of thinking about the subject. And from that, there's a multiverse that comes from string theory, which I find particularly exciting along these lines, which is called the Brain multiverse, not B-R-A-I-N, B-R-A-N-E multiverse. And it comes from the following idea. So within string theory, and I think many people have at least heard of what string theory is, it's this idea that the elementary constituents of matter are little tiny particles in the old way of thinking of things that are little tiny dots. The new idea of string theory is that within these little tiny particles there's something else, which is a little tiny filament that vibrates in different patterns. This little filament looks like a little piece of string, so the idea is that deep in the heart of matter there's little tiny vibrating strings. Now, as we've studied the math of this theory more and more, we've come upon the following very interesting idea. Within this theory, there are not only these little tiny filaments. There can also be what we call membranes, giant sheets, if you will, that can have 2 dimensions or even 3 dimensions and so forth. And the math seems to suggest that at least it's possible that all that we know about, every star, every galaxy, and so forth, is living its life out on one of these membranes. It would be a 3-dimensional membrane. That's very hard to picture, so let me just do a 2-dimensional analogy. Imagine a big slice of bread, where every star and every galaxy that we know about is on this slice of bread. That is our universe. Now, this proposal suggests that there could be other slices of bread, other membranes, other universes that, if you will, are all part of some grand cosmic loaf, to use the metaphor, with our universe just being one slice of bread, one universe in this grand collection. Now, to your question, why do I find this particularly exciting? Well, at the Large Hadron Collider, there's a chance that this proposal might be tested. How would that be? Well, the collider slams protons against protons at fantastically high speed. And the math shows that in some of those collisions, if there's enough energy, if they're moving fast enough, when the protons collide, they can create some debris that will get ejected off of our universe, off of our slice of bread. How would we know that? Well, the debris would take away some energy with it. That means there'd be less energy left for our detectors to measure after the collision than before. There'd be some missing energy. People are looking for these missing energy signatures, and if the energy is missing in the way that the math suggests that it should be, this would be interesting evidence that this brain picture is correct,
But
suggesting that there might be other universes out there.
have you been depressed recently?
Why do you ask?
Because you know that the LHC hasn't found anything at 7TV, so maybe at 14 they'll find it, but right now, as a lot of people may have heard, the results are negative on that. And they're also negative on something else, which I want to bring up.
Well, let me just respond to that, too. So, you know, it's very, very early. In fact, if they found anything at all, they wouldn't announce it because it'll take years of analysis before they do. But the important point, but you're making a great point. Not depressed, I'd be thrilled.
If it weren't
If it
found.
wasn't. Because this is meant to be an experimental science.
Right.
If we could rule out string theory, let me just be on the record very clearly about this. Would I be depressed? I would jump for joy. Because I'm not wedded to a particular theory. I'm wedded to working toward truth. I don't know what you think. I think you go around once. And if you go around once, I don't want to spend my time in this universe. I don't want to spend my time working on a theory that's incorrect. So if string theory is wrong, I'd like to know today. I'd like to know yesterday. So it's not a matter of having a certain emotional investment in one outcome or another. I have an emotional investment in contributing, however minimally that may be, to the ongoing human search for truth. And finding that a given theory is wrong is progressing because you can throw that one away, winnow down the possibilities. So depression, no. Excitement.
Good. So you'll always be excited whatever they find.
That, to me, is the nature of reality, nature of the universe.
Fine.
It is incredibly exciting.
The LHC has been running for a full year now. I think the end of March would be, 30th of March is when they started. Of course, they stopped for the break, and they create so many collisions every second. You know, it's trillions and trillions, and the data accumulates. They haven't found anything. So the first thing they ruled out, actually, at this energy level is extra dimensions. They're not saying that they don't exist, but they haven't found it. I want to lead in another direction in that, at least for a short while. I just heard from CERN that they haven't found any proof of supersymmetry either.
That's correct.
Just happened now. So as of now, with all the data they've collected in a year at half the energy they can reach, they haven't found any supersymmetry. And I think supersymmetry is another place where the mathematics and the physics might diverge. So let me add something. I'm not here to play your psychologist, but
I'm a little bit worried. How many people are really familiar with like ideas of supersymmetry
I'll explain
and things?
I'll explain it. Don't worry.
Okay. Actually, you know what? Let me just explain it first. Do a real
Fine.
Okay.
You don't trust me.
It's not that I don't trust you. I don't know. You live here. They can come and visit you. I just come here once in a while.
Fine.
So the full name of string theory is superstring theory, and the super, as you're referring
to,
hang on,
supersymmetry. I'm not talking about string theory.
And the full name of superstring theory, the super refers to exactly what Amir is talking about, which is supersymmetry. Now, what is it? Well, supersymmetry is a fantastically interesting mathematical symmetry that relates things that previously we thought were totally unrelated. You know, what is a symmetry? Now, if I take this glass and I begin to turn this glass around, it's highly symmetric, which means that no matter how I turn it, it pretty much looks the same. Each point is related to every other point in a way that suggests that none is special. Each can be turned into the other point by simply rotating it. Similarly, there are a class of particles in the world that are very important to us. They're particles that make us up. Electrons and quarks, the things that make up protons and neutrons. Those particles seem to be very different from a class of other particles by virtue of the fact that they actually spin around differently. Those particles that we all know about turn out to have something called spin half. That's the way these little particles spin. But there are other particles that we know about that have spin 1. That's like the photon or the particles that communicate the nuclear forces. And there are some hypothetical particles not yet seen that would have spin 0. They wouldn't spin around at all. Supersymmetry is a mathematical symmetry that would relate all of those particles. It would say that in some sense, each of those particles can be rotated into the others. Now, if that's the case, for that to be true, there will have to be a certain other class of particles, not yet observed, that the known particles we know about would turn into under this kind of symmetric rotation. Those are the supersymmetric particles. So for the electron, its partner under this kind of symmetry is known as the supersymmetric electron or the selectron. The quarks, squarks. Neutrinos, sneutrinos. I don't name them. For every known particle, there's a cousin called a sparticle. So what Amir is talking about, we're now looking for the sparticles. If they're there, it will confirm this idea. If they're not, it either means that we don't have sufficiently powerful accelerators to create these particles, or it may mean that they don't exist. That's the current state.
Right, it's a beautiful theory, but we don't know if it has anything to do with the real world.
We don't.
The problem with mathematics and physics goes back to Paul Dirac. Paul Dirac was a person who, a physicist, English physicist, who united quantum mechanics with the special theory of relativity. And when he did that in 1928, I think, something like that, he looked at his equations. Now, I'm going to sound like Brian. Maybe in another universe, I'm Brian. So I'm talking, what Brian says is we trust the mathematics. And that's what Dirac did. He was,
let me
finish.
I do not say we trust. I have to interrupt you if you're putting words in my mouth.
Okay.
I'm saying that
mathematics,
hang on, mathematics can be a potent guide for what we should consider interesting, what we should investigate further. But until observation, until experiment confirms it, no, I don't trust it.
You're
I
so
only
careful.
trust observation and experiment.
Fine. So Paul Dirac was sitting in front of a fireplace at Cambridge, and he looks and he realizes a way of uniting special relativity with quantum theory, creating quantum field theory, or relativistic quantum field theory. When he does that, he gets his mathematics, and I'm not going to put words in his mouth, and he looks at the mathematics, and the mathematics tells him that there are negative energy levels for the electron. And he says, well, maybe anybody else looking at it would have said, this is just the math. It's like when you solve an equation and you get two solutions. One is imaginary and one is real. You say, I'm going to ignore the imaginary. It's only the real one that's good for me in this particular real-world example. But Dirac didn't do that. He said there must be a particle that has these negative energy levels. And he called it, well, that turned out, first he thought it was a proton, and then he realized it's another whole new particle. So he was looking for new particles the way supersymmetry now looks for other particles. And that particle, the positron, or the positive electron, was actually discovered experimentally sometime later, a few years later. So the point is, sometimes it works, but it doesn't work all the time. As the example of Heisenberg. So I'm glad you're open-minded. You're saying we want to follow the mathematics, and we are in experimental science. We want to see where it leads us. But the problem is, and I think it's a sort of disappointment to a lot of physicists, because a lot of physicists today believe in supersymmetry more than, or follow supersymmetry a lot more than other theories. So if we don't find these particles, that means here's a symmetry. It's a beautiful mathematical construct that may have absolutely nothing to do with this universe or any other universe.
That's right. So ultimately, nature speaks, and it speaks through experiment and observation. But you're right, there's a large segment of the theoretical community that takes this idea very seriously. We have been working on it in one way or another since the 1970s. So if these particles are found, scientists around the world will be popping the champagne corks. This will be an exciting moment where the example you just gave of Dirac would be recapitulated in a very big way. If these particles are not found, we will accept that as the way the world works and go back to the drawing board. And that, to me, is thrilling.
Good. Fair enough. So how about the other theories? Tell us about some of
the other ways that you can get to multiverse theories.
Right.
Well, another simple one is one that comes out of thinking very carefully about the Big Bang. So again, we touched on the Big Bang earlier, which is this idea that the universe underwent this rapid expansion early on. But one of the things that perhaps we don't emphasize enough when talking in general context is that the Big Bang theory actually leaves out something pretty important, which is the bang. The Big Bang theory tells us how the universe evolved from a split second after whatever started the outward swelling to happen in the first place. But it doesn't tell us what caused that swelling to actually occur. Now, people have been working very hard to fill in this gap. And the reason I bring this particular gap up is because there is a proposal now for what caused the outward swelling. It's called inflationary cosmology. It's basically the recognition that goes back to Einstein that gravity in certain circumstances can be repulsive. We're used to gravity being attractive. You drop the glass, it falls because the earth attracts it. You drop the ball, it falls, again, because the earth pulls things together. That's what gravity does. But actually, Einstein showed, surprisingly, that under exotic circumstances, gravity can actually push things apart. The belief is that, the possibility is that in the early universe, that exotic environment was realized. There was an energy suffusing space that gave rise to repulsive gravity that pushed everything apart. That's why the universe started swelling in the first place. The thing is, when you study this theory in detail, it seems to show that this outward swelling would not have been a unique one-time event. It says that there could be many of these Big Bang-like beginnings at various and distinct locations in a much larger cosmos, each giving rise to a swelling realm, each giving rise to an observable universe, and a universe that people like us could inhabit, but there could be universes upon universes upon universe. This is the inflationary multiverse. And the nice thing about this approach is that the idea that space underwent this rapid swelling early on from this repulsive gravity, that has been subjected to some very interesting observational tests. If the universe went through this rapid swelling early on, here's what would happen. Little tiny quantum jitters, quantum fluctuations in the young universe would be stretched out by the rapid swelling and smeared out across the sky. An analogy is if I had a little balloon with a fine-tip pen. Imagine I wrote a little message on the surface of the balloon. You couldn't actually see it, it's too small. If I blow air into the balloon, as the balloon stretches, my message gets smeared out across the surface of the balloon. Now you can see it. Now the tiny quantum jitters in the early universe may behave similarly. They're like the little message. And as space underwent this rapid expansion, that message gets smeared out across the sky as tiny temperature differences in the heat left over from the Big Bang. It's called the cosmic microwave background radiation. And we have measured this heat left over from the Big Bang, and the way the temperature varies from point to point is exactly in line with the mathematical calculations.
But
and that is a very convincing piece of evidence for at least taking this theory quite seriously.
I think the theory is taken very seriously by most, not only cosmologists, but even astronomers and, and physicists. Yeah. The question is, does it really imply the existence of something that's unobservable as of now, which is a multiverse? I think that those microwave fluctuations, and as they expand, and I think there are galaxies that are spawned from them as well. And,
sure.
Does that really imply, other than the mathematics, you keep going back to the mathematics, doesn't mathematics really tell you that if you see this picture of the microwave background radiation in space, you must have a multiverse?
No.
Okay.
Not must. And that's why I'm not here saying that these ideas are proven. You may recall, when we started out this conversation, I emphasized that these are speculative ideas that come from our investigations. And until we have observation of them, we can't believe that it's real.
Let me ask you,
but let me just take it a little bit further. But what happens in the subject is, when you have a theory that is able to describe things that you can see, it bolsters your confidence to follow the theory further. That's where the confidence comes from, to follow the math further. Now, does the math uniquely imply that there have to be these other realms? No. There are versions of the inflationary theory where there'd only be one realm. They're very hard to come by. They're very cumbersome. They feel very contrived from a mathematical standpoint. That doesn't mean they're wrong. They could be right. But the ones that don't have that contrived quality are the ones that do give rise to these other universes. So do we know that they're there? Absolutely not. But does this suggest this as a compelling possibility that's worthy of further study? Yes. And how would you know it? What sort of experiment might give you some insight? Well, here's, again, rhetorical. So if you had these... if you had these expanding realms...
I'll shut up if you want me to.
Not at all. If you have these expanding realms, imagine it, as a big cosmic bubble bath of different universes, with our universe being one of those bubbles. Now, in a bubble bath, the bubbles can collide. Similarly, these universes, as they expand, can collide too. If they form close enough together, they can smash into each other. How would we know that if our universe had a kind of fender bender with another universe in the past? Well, that collision can send ripples through this heat left over from the Big Bang, this cosmic microwave background radiation once again. So scientists are looking in that background radiation to try to find finer patterns in the temperature variations in space that might indicate that we got hit by another universe. Is there any positive evidence yet? No, not yet. The collisions could yield a signature that's too small for our current level of technology to access, or maybe it never happened. But that's the way in which, in principle, you could have observational evidence of a universe that you can't literally see. You see its effect in our universe.
Can I speak now?
So please.
So how would you know? There have been several generations of satellites looking at the microwave background radiation. And we know a lot about the microwave background radiation. In fact, it's uniform to 1 in 10 to the 6 or something like that. The fluctuation is very, very small.
Right.
How would you be able to tell? I mean, you got to give us something concrete. If you say, here's a universe and here's another universe and they collide. You know, you lost me at the beginning because I don't think another universe can exist on this axis. It just because of the fact that we created this space. What is this space? You haven't answered my question on that, but let's leave that out. So hold on, let me finish. So you crash these.
But you're giving the impression that there's something missing, and the missing part is actually you're not fully comprehending the idea because we're talking about in very general terms.
I know what you're thinking. There's the hyperspace there and the
hyperspace.
Calabi-Yau manifold, and we're.
Knowledge can be a dangerous thing. You sort of know too much right now.
I would apply it to you, Brian.
This has nothing to do with hyperspace, nothing to do with extra dimensions. Bread and butter cosmology that takes place in the ordinary dimensions have this possibility. So let me just describe it. So the wider cosmos that you're having trouble grasping, think of it as a big sauna, a steam
It's in
bath.
R3. It's in three-dimensional.
R3, yes, 3 dimensions. Let's just stay simple. So 3 dimensions that's filled with this dark energy that causes the outward repulsive gravity that I was referring to. What happens is, region by region in this big cosmos, the energy can degrade. And as the energy degrades, holes open up in this wider cosmos where the energy turns into particles that make stars and galaxies. So our universe is simply one of these regions where the energy has degraded. The inflaton energy has degraded. The image that works pretty well is, think of a block of Swiss cheese. Imagine that the cheesy part of the Swiss cheese is where this energy exists and is forcing things to experience gravitational repulsion. The holes in the cheese are places where the energy has degraded, where stars and galaxies can form. So the different universes that I'm talking about are just the different holes in this big expanding block of Swiss cheese.
So they're really one universe.
Whatever language you'd like.
Fine.
Again, as I said early on,
let
me just say, as I said early on, the language is confusing.
Fine. Let's leave it at. Let me ask you. We're talking about experimentally detecting the evidence of the multiverse.
Yes.
Whatever the multiverse may mean.
Yes. Exactly.
Blue cheese or Swiss cheese.
Yeah. Good.
So you've got these two universes colliding.
Yes.
And here's the background radiation.
Yes.
It's fluctuating.
Yes.
How do you know it's from that and not from something else?
That's a question you face with all experimental data. When you look at data, you say, what's the best explanation for it? And you try to rule out all other competing proposals, and the proposal that stands up and is the best explanation is the one that you gain confidence in. So we've done calculations, and actually I have not done these little calculations myself. Others should get the credit for it. But other physicists have done calculations of what would happen to the microwave background radiation under this process. And they have very explicit predictions for what would happen to the radiation plots of how the temperature would vary from place to place. And if you find temperature variations in line with those predictions, and there's no other competing explanation, then indeed your confidence in this possibility would rightly grow. That's the way science works.
Fine. Let's assume it will happen someday, and then we'll have proof of it. But until then, of course, we don't know.
I agree with you completely.
Tell us about some of the other multiverse theories.
Well, let me just ask you, what time is it? Because I think we've been going on.
It's 8:10.
Are we only no, only because I don't want to make sure that people get a chance to interact if they want to. I don't know what the format here is, but you tell me. I'm happy to keep on going. I got no place to go tonight, but whatever you want to do.
I guess you got your answer.
So yep, carry on.
No.
Actually, anybody have a question? Want to throw anything out?
He's tired of my question.
If we'll take some time for some questions now. We have 2 museum staff members with microphones who will be walking up and down the aisles. We'll select you, and when we do select you, please stand up and don't begin talking until you have a microphone. So we're ready for some questions now. First question down here.
I know this field moves very quickly, but in 2006, Lee Smolin, a theoretical physicist at the Perimeter Institute in Canada,
Yes.
Wrote a book entitled The Problem with Physics.
The trouble with physics.
Trouble with Physics, excuse me.
Yeah.
And it seems to be that he has basically abandoned string theory. So chiefly because of lack of experimental confirmation.
Yes.
So my question is, has he abandoned it too early because of this, or Can
Yeah.
this carry on to future?
It's a good question, and Lee's a good friend of mine, and when I speak to him, he says largely he thinks his book has been somewhat misinterpreted. What he claims that he was really meaning to say in that book was that string theory is not the only approach to putting together quantum mechanics and general relativity. There are other approaches. In fact, he's a champion and has been one of the founders of a competing approach called loop quantum gravity. And part of what he was saying was he feels that too many people work on string theory, not enough people work on loop quantum gravity, and the health of the field would be advanced if there was a more balanced approach where more people worked on these other approaches and string theory wasn't sort of the primary one that was looked upon as the solution in the physics community. I agree with that. I feel that health of a field is evidenced by all sorts of different ideas. The reason why more students work on string theory, frankly, is I think it's a more attractive, a more appealing, a more promising approach. I think that's how graduate students make their decisions. But, I full well agree that it would be great to have active centers of research in all these approaches. And he helped found the Perimeter Institute that you mentioned, and there are a lot of people there working on loop quantum gravity. So the idea that he abandoned string theory, he's not really a string theorist. I mean, he's worked on it from time to time because he's one of the folks who really tried to cross over. Maybe there's a way of doing loop quantum gravity and string theory, melding them together. He and I have discussed this. That would be great if that happened. But his main point is that there are other approaches and they deserve attention. On that point, I would agree.
We have a question over here.
Hi. Yeah, my question is related to the many worlds theory. Basically about the fact that, like, right now in another world, like, I don't know, I could be asking a question to someone else. But whose world is it? Like, if we're making these choices, like, are we creating these worlds? And, like, so whose world is this? Whose world is the other world? Is it yours? Is it mine? Is it someone else's here?
Yeah, well, according to the bread and butter many worlds approach, as Hugh Everett wrote down, as others have developed it since the 1950s, if you're in a situation where quantum mechanics says there's a possibility of this, a possibility of that, a possibility of this, and so forth, all of those possibilities happen. It's not really a matter of you choosing which happens. The mathematics doesn't allow any possibility to go unrealized. All roads are traveled in the quantum multiverse. It's funny, I'm teaching this right now. I'm teaching undergraduate quantum mechanics, and I'm literally, this week, we're talking about the many worlds approach, and we set it up last week. And it is, if you actually go through the mathematics of it, which very few people I've found actually do. Few people actually go back to the 1957 paper and read it. Few people go back to the thesis that Hugh Everett wrote down back in the 50s and read it. Have you actually read his thesis? I mean, his thesis is a mathematical gem where he makes a very potent case for this idea. From a modern perspective, as we were discussing, I don't want to sort of open it up again, I think there's still things missing. But when I read his thesis, I'm taken along, and I'm very critical of it, because sort of like Amir, it's an idea that I don't think is right, but I'm taken along by the mathematical argument to sort of the last step. And the last step, I think he didn't quite get right, and I don't think anyone, in my opinion, has yet filled it in. But others disagree with me and say that the last step has been filled in. But if it's correct, all possibilities allowed by quantum physics actually happen. Sometimes I'm asked by this one and describe about, does that mean that, like, there's one universe where, like, Sarah Palin is president, And I have to tell them, it has to be compatible with the laws of physics.
Next question over here.
So you mentioned some of the other potential quantum gravity unifications, like Topos theory and loop quantum gravity. Do any of them have any implications as far as the multiverse goes?
It's a good question. I don't know enough about them, I have to say, to answer that with any degree of confidence. In all of them, quantum mechanics is part of the story. So if the quantum multiverse is true, then I think all of them will likely embrace it in the manner that we've been discussing. So from that perspective, yes. In terms of the other multiverse ideas that we've discussed here today, I'm actually not sure what they have to say about it.
Question over here.
In your many bubbled world,
Yes.
We know that after the Big Bang, certain specific criteria had to be met, or the universe would have flown apart
Yes.
and the particles. So in the other worlds, do they had to follow our laws in order to succeed, or did some of them die, or what? How does that work?
Yes, so one of the deep questions that we have faced over the last 15, 20 years is aligned with exactly what you're asking. We have gone out and measured certain features of our universe, certain numbers, certain parameters, like the electron's mass, the strength of the electromagnetic force, the strength of the gravitational force, the masses of the quarks, and so forth. And what we found is that we understand the numerical values that the experiments are revealing, but we haven't been able to explain why those particular values have been found. Now, you might say, should we care if the electron was a little heavier or a little lighter? Maybe that's just one of those details. You shouldn't really worry about it, but you should for exactly the reason that you ask. If those numbers had been somewhat different, then the universe as we observe it and know it wouldn't exist. If I had a machine up here with 20 dials, and I call in someone randomly to come up, and you make gravity stronger, or you make the electromagnetic force weaker, for almost any fiddling that you do, the universe does not evolve in the way that we know it. Stars don't form, planets don't form, and it's hard to imagine how life would exist in such a universe. So the deep question has been, why do those numbers have just the right values to give rise to the universe that we are familiar with? We have hit a dead end so far in trying to answer that question. The multiverse casts a very different way of thinking about that question. It's really along the lines of what you suggest. The idea is maybe there are many, many, many universes in which those numbers vary from universe to universe to universe. And in most of those universes, we couldn't exist because the stars wouldn't be there, the planets wouldn't be there, and so forth. And the answer for why the numbers have the values that we observe is we couldn't observe any other values. We couldn't exist in those other realms. And that is an approach that may ultimately hold water. Now, let me just give you a little analogy on this that happened to me two years ago with my 4-year-old, which I think helps one understand this a little bit more. You know, my son is 6 years old now. He was about 3.5 or so. We went to a shoe store. And we'd gone to shoe stores before, but this is the first time he was really old enough to begin to think about what was happening. We go into the shoe store. The guy measures his shoe, goes in the back, comes out with the shoe, puts it on, it fits, we leave. Everything's happy. My son turns to me in the street and he says, "Wasn't it lucky that they had my shoe size?" And as I probe further, I realized that what he had in mind was that shoe store had a single shoe size, and it just so happens that it fit his foot. What a mystery that would be. But when I explained to him that back in the stockroom there were many, many, many different shoe sizes, and the guy just picked out the one that he'd measured, the mystery went away. What's the moral? The moral is, if you think there's a unique object that you're trying to explain, that can be mysterious. But if you then realize that it's not a unique object, it's one of a vast collection, the mystery can evaporate. That may be true with these parameters. Just as we found the shoe size that fit his foot, we find a universe where the parameters fit our existence. And that may be the answer.
All right, I guess preface this question, I guess I'm going to ask if you're familiar with, I think his name is Ronald Mallet and his time machine experiment.
Sorry, I don't.
I guess he's a theoretical physicist out of was it Stanford University in Connecticut, right? Yeah. I guess he postulates that if you twist light enough that you can twist space-time sufficiently to create like a essentially
closed time-like curves, we can go back in time.
Right. Well, yeah. At least send like a subatomic particle stream back through time to when the machine was turned on.
Okay.
Can't go back before the machine was turned.
Sure.
Right. But if such a machine were actually built, could something like that possibly be used to maybe test some of these theories?
Oh boy. You know, you talk about speculation. We're now in speculation squared or something here. You know, how would time travel interface with some of these ideas? Let me just turn it in that direction, and I'll simply say this. One of the big puzzles with time travel, of course, is you go back in time and you affect things in a way that maybe prevents your own existence. You go back and you kill your parents before you were born, and there's a logical paradox. You know, we've seen this played out in Back to the Future. You know, Hollywood loves this idea. You know, there's a variation on the paradox, you know, which comes from the following idea. I mean, imagine you know, that you travel, imagine you can travel to the future, you know. Imagine I travel to the future, let's just say, and I want to see what's happened in string theory, you know, has it been proven or not, and so forth. So I go to the library or the floating internet station, whatever, and I see that, surprisingly, the theory has made a major advance, and the author of that paper is my mom. And I'm like, that's weird because my mom doesn't like physics, she doesn't know, wants me to be a doctor, you know, not this kind of doctor until I am a doctor, you know, all this sort of stuff. You know, and I look in the acknowledgments to the paper in the future, and she thanks me for teaching her all this physics. And I'm like, holy crap, I better get back, I got a lot of work to do. She doesn't know very much, you know. So I use her little machine, I travel back, and I start to tutor my mother, and man, it's not going well, you know. She's not getting it. A year goes by, 2 years. I'm like, how in the world is she ever going to write that paper? You know, and then I said to myself, I know what was in that paper. I read it. Let me just tell her what to write. So I tell her what to write, and she writes the paper, and everything turns out in the future as I had it. Now, the question is, who gets the credit? Now, you know, it's not a question of credit, really. It's a question of where did the information come from? Did she think of it? No, she got it from me. Did I think of it? No, I got it from her paper. So information, ideas seem to just sort of pop in from thin air if these things are possible. Now, how does this relate to multiple universes? Coming back to that. Here's the possible, fanciful idea that people have floated. Imagine that when you travel to the past, for instance, you never come back to your own universe. You come back, say, in the quantum multiverse, let's use that as an explicit example, you come back to one of those other copies of our universe. So for instance, if I go back in time and kill my parents before I'm born, I wouldn't be born in that universe, but so what? My origin would still be unaffected because my parents would be unaffected in the universe which I started. So that's sort of, but again, it's a little far afield, but at least that's some interaction with time travel.
Question over here.
I just had a question about something I'm recently aware of, the Bose-Einstein condensate theory. And it's something that physicists now, we are so lucky to live in a time when people can produce a Bose-Einstein condensate in certain elements. Now, if they can, hypothetically, if they could create that instant in a room, assuming that, let's assume they can't, is that, do all the basic theories of quantum mechanics break down? If you have a situation,
do you want me to answer?
One of you people explain the Bose-Einstein
I don't think it does that. Brian will be the final arbiter. But I think that Bose-Einstein condensate was created right here at MIT. It was also created in Colorado. Yeah, so around the same time. A Bose-Einstein condensate is just you cool something, you cool some atoms to a very, very low temperature. And what happens is the wave, every particle is a wave also. So the waves overlap. So you're really creating quantum mechanics for a large object, in this case a collection of atoms. I don't think it relates to anything else we've been talking about. But
yeah, and it really comes out of basic quantum mechanics, so it's not incompatible with it.
And those waves jump to one point. I mean, that's a basic principle.
Pardon me?
If you actually reach a Bose-Einstein condensate, all of those waves become one point. They jump to one point. Well, that's what the physicists at MIT say.
I personally wouldn't describe it that way, so I'm not sure what they have in mind when they say it.
Physicists at MIT describe it that way.
Okay. Yeah, I'm not sure exactly what they had in mind, so it's
well, they describe it that way.
Okay.
We have time for one last question over here.
Yes, excuse me. I should preface this by saying I'm a diehard mini-worldser, and so the questions make most sense if you like that. I was impressed by an observation in your first book, where you noted a duality between length and a 1 over length time, 1 over a time, which seemed to have a special meaning, if I understand this correctly, at about 1 Fermi time after the Big Bang, when the energy for a wound and unwound string are about the same. And there was something, I don't recall the details now, but something that you said there in the notes prompted this idea, and I'd like to know if anyone's pursuing anything like this.
Okay.
And that is that if you imagine that there is a moment, perhaps it's this 1 Fermi time after the Big Bang, of perfect symmetry, and I mean 0 microscopic entropy at that point also, a finitely describable universe that is now mini-world style, going to evolve perhaps 10 to the 500th vacuum states, or whatever it takes to get us forward to all the different versions of us here now, and Schrodinger with his dead cat and Schrodinger with his live cat. we could look at the same thing. You'd expect the same thing to be happening in that one-over interpretation going back towards the moment of the so-called Big Bang.
Yeah.
And now that singularity turns into an illusion. It's like the singularity at the North Pole. It's an accident of using an inappropriate set of axes to describe what happened to that first little thing. So here's this image of us, and we have another doppelganger now, which is the whole multiverse repeated back in that first little moment of time.
Yes. So
I'm curious if anyone's pursuing ideas, anything like that.
So it is one of the most surprising features of string theory, which shows that under the circumstances largely that you're recounting, a universe that's bigger than, let me call it the Planck length, not the Fermi scale, the Planck length, bigger than the Planck length and expanding is actually equivalent to a universe that's smaller than the Planck length and contracting. That's the R and 1 over R worlds that you're talking about. I wouldn't use the word doppelganger or image to describe these two realms. They're really distinct mathematical descriptions of the same reality. So it's really just two different ways of looking at the same thing, even though they seem vastly different. But as to your question, how would cosmology look and how would the singularity look in this picture? Yes, in fact, right here at Harvard, Kurman Vafa and another cosmologist named Robert Brandenburger, they studied cosmology in the context of this universe that had that one R goes to 1 over R symmetry. And they did find something along the lines of what you're suggesting. So what is the singularity? So if you run the universe back and back in time, it gets denser and denser and denser. Way back at the beginning, the density soars to infinity. They found that in this setup, when the universe gets smaller than a Planck length, that's about 10 to the minus 35 meters. When it gets smaller than the Planck length, the temperature levels out, and as the universe gets smaller, the temperature starts to turn down because of this very symmetry that you're talking about. It never spikes to, it never spikes to infinity. There's never a time when the density grows infinitely big. So this is a cosmological model that has been proposed based on that symmetry. There are other things that it doesn't describe yet, so there's much work that would need to be done to take it fully seriously. But as a toy test case of a cosmology where there wouldn't be a singularity, yes, it's one of the most potent ones that's come out of string theory.
Do we have time for another brief comment, question? I just wanted to point out that if you're taking that kind of a model seriously, then our current event horizon would be represented by all of the possibilities in the many worlds that could have happened to this point over this space. And now if we want to get in our imaginary spaceship and go out much farther, everything that's happening there is just the same set of things. And what we're doing is we're kind of getting an outer product of all these combinations. When we go out there and wait long enough to see what's out there, if that were allowed, we're really just sampling what's happening in another branch of the universal wave function here. And so now this gives you another way to wrap that infinity so that it's not infinite. When you've described one event horizon, you've described everything. And it will look like an evolving infinity to an embedded observer, but you don't have this problem of what do we mean by infinite.
Yeah, and that's rooted in the fact that we're talking about the radius of a circle, which is, of course, of finite size. So this is an example where you have a finite universe, not an infinite one. So indeed, you're right. You would not have this problem that we were tussling with earlier on. But absolutely. It can, yes, absolutely. More questions? Oh, well, I'm sorry, are we done?
Well, I was going to say, I think our time is up, but thank you so much for that wonderful, lively, and very mind-expanding conversation. Brian.